All right, today we're going to dive deep into a piece of heavy machinery you see all the time, but probably don't think much about, the concrete mixer. But this isn't just any mixer. We're going to look at the incredible engineering masterclass it takes to turn one of construction's loudest, dirtiest machines into a silent, smart, hybrid powerhouse. Believe me, this is way more than just slapping a battery on a truck. It's a story of overcoming some serious physical challenges with some truly elegant engineering.
Okay, so this right here, this chart gets to the very heart of the problem. You've got this enormous 300 kilowatt diesel engine, an engine powerful enough to haul 24 tons of truck and concrete down the highway. But then it gets to the job site and spends hours just idling, using only 30 kilowatts of that power to do its main job, turn the drum. That's just 10% of its capability. From a systems point of view, it's the very definition of inefficiency, just burning fuel, making noise, and pumping out emissions for no good reason.
So how do we fix this? Well, the modern engineering answer is what we call a P2 hybrid plus ePTO architecture. Now, what does that mean? P2 just means we place an electric motor right after the engine, and ePTO is an electric power takeoff. This setup brilliantly decouples the mixing drum from the diesel engine. The result? The truck arrives, the diesel engine can shut completely off, and a high-voltage battery takes over, powering the mixing silently and with absolutely zero emissions on site. So what this architecture really does is create two separate, independent systems inside one vehicle. You've got the diesel engine, which is now optimized for what it does best, driving. But once the truck is on site, the electric motor and battery system take over the mixing. This fundamental split, this separation of duties, is the absolute key that unlocks all the incredible efficiency and performance gains we're about to talk about. But, getting there is not easy. This isn't like electrifying a passenger car. A construction site is one of the most brutal operating environments on Earth. So for this to work, our system has to conquer three pretty massive engineering challenges. And each one of these pushes the boundaries of design, materials, and just pure ingenuity. So our first big challenge is all about the physical integration. We call it wiring a twisting frame. Now, to get a picture of this, imagine trying to install a really sensitive, high-voltage electrical system onto a wet towel, right as someone is wringing it out. Seriously, that is the kind of mechanical stress a truck chassis goes through every single day on an uneven job site. And that brings us to a huge engineering question. The truck's frame is built to flex. It has to. It's carrying a 24-ton load of sloshing concrete. So how in the world do you run a 400-volt power cable along that frame without it getting stretched, crushed, or rubbed raw? Any of those could lead to a catastrophic failure, and the forces at play here are just immense. Well, the solution starts with a super strict set of rules for routing these cables. And as you can see here, these aren't just suggestions, they are non-negotiable principles for safety and long-term reliability. Let's just take the bend radius, for example. If you bend a high-voltage cable any tighter than 5 times its own diameter, you can create tiny, invisible microfractures inside. You can't see the damage, but over time, it weakens the insulation and could create a very dangerous short circuit. And this is the final brilliant piece of the solution. It's a surprisingly low-tech answer to a very high-tech problem, something called a service loop. Engineers intentionally build this S or omega-shaped bend into the cable right where it crosses a flexing point. This simple little loop just acts like a spring, soaking up all that twisting and bending so that the cable and its connections are never under any stress. It's just a beautiful, simple piece of mechanical problem solving. Okay, on to challenge number 2, environmental survival. We're not just talking about a little rain or mud here. We have to design for corrosive concrete dust, which has a high pH, followed by a daily cleaning ritual with high-pressure, high-temperature water jets. It's this brutal 1-2 punch of chemical attacks and extreme thermal shock. Now, to really get the scale of this, let's do a quick comparison. Your smartphone? It probably has an IP67 rating. That means it can survive being dunked in a meter of water. That's nice. The components on this mixer have to meet the IP6K 9K standard. This means they survive getting blasted with 80 degrees Celsius, that's 176 Fahrenheit, water jets at a pressure 100 times our atmosphere. It's less like a dip in a pool and more like getting hit with a flamethrower and a fire hose at the same time. But here is where the physics gets really weird. The very act of cleaning the truck can actually destroy it. See, when the electronics are running hot, the air inside their sealed metal boxes expands. Then, a pressure washer hits that hot box with cold water. The air inside cools down and contracts instantly, creating a powerful vacuum. And that vacuum is strong enough to literally suck water vapor right past the toughest seals. The component actually breathes in water, which is a disaster for high-voltage electronics. So what's the solution? Well, it's an incredibly clever bit of material science actually borrowed from your high-tech sportswear. Engineers install a tiny breathable vent made from a membrane, think Gore-Tex. Its microscopic pores are just big enough for air molecules to pass through, so the pressure always stays equalized. No vacuum can form. But those same pores are far too small for the bigger water molecules to get in, so the box can breathe without ever drinking. Pretty smart, right? All right, this brings us to our final and maybe the toughest challenge of them all, thermal management. See, unlike a regular electric car that gets cooled by air rushing over it as it drives, a concrete mixer does its hardest work when it's standing perfectly still. There is zero cooling airflow. This is what engineers call the ultimate thermal nightmare. Zero-speed, high-load operation. You've got the electric motor generating a ton of heat as it churns that heavy concrete, but because the truck isn't moving, that heat has absolutely nowhere to go. The whole system is at risk of just cooking itself. And to put a number on it, the motor and its inverter are kicking out between 6 and 8 kilowatts of pure waste heat. To give you some perspective, that's like having 4 electric kettles constantly boiling water inside a sealed box. All of that heat has to be actively pulled out of the system with a liquid cooling loop. Now, the solution here isn't just about adding bigger fans or radiators. It's about intelligence. It's a software-driven strategy. The system is constantly monitoring temperatures and adjusting the coolant pump and radiator fan speeds in real time. But the most critical part is that last step, derating power. If the system gets close to overheating, it doesn't just shut down. A shutdown would be a catastrophe. You'd end up with tons of concrete hardening inside the drum. Instead, the software is smart enough to slightly reduce the motor's power, just enough to stay safe while still keeping that all-important drum turn. So when you solve these 3 huge challenges, the mechanical twisting, the environmental assault, and the stationary heat, what you end up with is more than just an electric mixer. It's a fundamentally smarter, more capable machine in every way. The benefits really are transformative. I mean, you get silent operation, which is a total game changer for building in cities. You can cut fuel use by over 50%. On-site diesel emissions, gone. But here's the coolest part, something nobody expected. The electric motor is so precise that it can feel the concrete's consistency just by measuring the torque needed to turn the drum. It turns the entire mixer into a rolling, real-time quality control lab, making sure the concrete mix is perfect every single time. And this really brings us to a bigger, more strategic question. If this level of systems engineering can turn a humble concrete mixer into a silent, super efficient rolling science lab, it really makes you wonder, what's next? What other essential, heavy-duty machines are just waiting for this same kind of brilliant transformation?